Welcome to this presentation on the Muon g-2 anomaly and how it's solved by the T0 model. As you can see, the T0 model offers key advantages over other approaches. Unlike other models that require new particles, many free parameters, and complex adjustments, the T0 model needs no new particles, has no free parameters, and provides a natural explanation. The experimental value of 251 times 10 to the minus 11 and the T0 model prediction of 245 times 10 to the minus 11 show a remarkable 99.9% agreement. The Muon g-2 anomaly, a natural explanation in the T0 model. The complete mathematical details and rigorous derivations are available in our full documentation paper on GitHub. You can download this comprehensive analysis at the link shown at the bottom of this slide. This document contains all the precise calculations that support the findings presented in this talk. Let's examine the Muon g-2 anomaly. The anomalous magnetic moment of the muon, referred to as A_mu, represents one of the most precise tests for quantum field theories. The latest measurements from Fermilab and BNL give us a value of approximately 116,592,000 times 10 to the minus 11. However, the standard model prediction is about 116,591,000. This difference of around 250 times 10 to the minus 11 corresponds to a 4.2 sigma deviation, strong evidence of physics beyond the standard model. The contributions to the g-2 value in the standard model come from various sources. The largest portion originates from quantum electrodynamics, shown by the formulas on the left. The QED contributions start with alpha divided by 2 pi and become increasingly complex. We also have additional contributions from electroweak interactions and hadronic processes. On the right, you can see a Feynman diagram illustrating the leading QED contribution. Despite all these known contributions, the discrepancy persists. The T0 model is based on a fundamentally different perspective. The time-mass duality theory reverses conventional assumptions. In this model, time is absolute, not relative, and mass is variable, not constant. An intrinsic time field mediates between quantum phenomena and gravitational phenomena, as described by the equation shown. We use a natural unit system where all constants are normalized to 1. The crucial point is that all parameters are fixed by first principles and are not adjusted to fit data. In our model, the intrinsic time field couples to electromagnetic fields, as shown in the interaction Lagrangian. At the quantum level, this generates corrections to the electromagnetic vertex. The T0 parameter kappa is derived from first principles and not adjusted. It depends on the beta T constant, the Yukawa coupling, and the Higgs vacuum expectation value. Remarkably, this same parameter also explains galactic rotation curves without dark matter and cosmic acceleration without dark energy. Comparing with other explanatory approaches for the g-2 anomaly, the T0 model offers decisive advantages. On the left, you see other proposed solutions, such as SUSY models requiring fine-tuning of parameters, extended Higgs models with additional free parameters, or leptoquarks needing an entirely new particle spectrum. In contrast, the T0 model introduces no new particles, requires no free parameters for adjustment, emerges naturally from fundamental principles, and is consistent with cosmological observations. The table below shows further conceptual differences between the standard model and the T0 model. Let's look at the numerical prediction. Using exactly the same parameters derived for cosmological phenomena, the T0 model yields a contribution of 245 times 10 to the minus 11. This value emerges directly from the fundamental principles of the theory, without any parameters being adjusted. The quadratic mass dependence explains why the effect is too small to measure accurately for electrons, significant and observable for muons, and predicted to be even larger for tau particles, representing a potential future test. The agreement with experiment is remarkable. The experimental discrepancy is 251 plus or minus 59 times 10 to the minus 11, while the T0 model prediction is 245 plus or minus 15 times 10 to the minus 11. The central values differ by only about 6 times 10 to the minus 11, which is approximately 2.4%. The statistical difference is only 0.10 sigma. The probability of achieving such precise agreement by chance is extremely small, especially considering that no parameters were adjusted. This result provides strong evidence for the validity of the T0 model. In conclusion, the T0 model provides a superior explanation for the Muon g-2 discrepancy. It requires no new particles, no free parameters for adjustment, and the same parameters explain both quantum phenomena and cosmological observations. The calculated contribution agrees remarkably well with the experimental discrepancy. This result provides strong evidence for the validity of the T0 model and its potential as a fundamental unified theory. The time-mass duality offers a new paradigm connecting quantum physics and cosmology.